Just a friendly reminder that Minnie doesn't take life too seriously, so neither should you. Just have fun and let's go enjoy some math.
Okay, let's go ahead and get started. So today we're going to be going over a fairly simple proof that the square root of 2 is an irrational number. In order to do that, we have to establish what an irrational number is. And before we can do that, we have to establish what a real number is. Okay, so a real number is any number that can be seen on the number line. Now, this is a pretty dramatic oversimplification. However, there's no way I can go over the entirety of the real number system in this video, as there's an entire field of mathematics dedicated to studying the real numbers. So we're just going to do a very simple overview. And for today, we can assume that the real numbers are any numbers that can be represented on the number line. Okay, so let's go ahead and draw our number line here. And on the number line, you're going to find numbers like 0, 1, 2. You're going to find -1, -2. So you're going to find the integers on the number line. Okay. You're also going to find fractions on the number line. So numbers like 1/2, -1/2, and really any number you can represent as one integer over another integer. Okay, so we might find 3/2, so on and so on. You get the idea. But we call these numbers rational numbers. Okay, so let's go ahead and define what the rational numbers are. So we can say the rational numbers is the set of all numbers that can be written as P over Q, such that P and Q are both integers. Okay, that is our rational numbers. Okay, and any number that is not an element of the rational numbers and is on the real number line is an element of the irrational numbers. So our goal for today is to show that the square root of 2 is an irrational number. Now, what's interesting about this particular proof that I'm about to show you is with just a couple of tweaks, you can show that the square root of any prime number is irrational, meaning it is not an element of the rational numbers. So before we get started on this particular proof, there are a couple of things that I have to go over. One is this concept of the greatest common divisor. Okay, now the greatest common divisor is denoted GCD, or greatest common divisor, and it is often comparing two numbers or multiple numbers, but we'll just say two numbers P and Q. That's normally how it's written. Okay. So the greatest common divisor of P and Q. This means you're finding the largest integer that can divide both P and Q evenly. So let's do an example. So we have the greatest common divisor of 2 and 4 is 2, because 2 is the largest number that divides both 2 and 4 evenly. Okay? Okay, and another essential element to this proof is this theorem that says that if you have an integer, the parity of that integer is preserved when you square it. So what this means is that if you have an integer p and it's even, this implies that p squared is even. Okay? And if p is odd, this implies that p squared is odd. Okay? I may go over a proof of that, this particular result, at some later date, but for today we're just going to assume it as given for this particular proof. Okay, I think that's all we need to know, so let's go ahead and get started with the proof. So this particular proof is going to be a proof by contradiction, okay? So what that means is we're going to start by assuming the opposite of our ultimate goal, okay? So we're going to assume that the square root of 2 is rational. So we're going to assume that square root of 2 is an element of the rational numbers, okay? And what this means is that the square root of 2 can be written as p over q, where both p and q are integers, okay? Now, we're also going to assume that the greatest common divisor of p and q is equal to 1. And what this means is that this fraction, p over q, is reduced as much as it can be reduced. So it cannot be reduced any further. So it couldn't be of the form 2 over 4, because that could be reduced to 1 over 2. So we're assuming that it is reduced all the way. Okay? So what we're going to do is we're going to take this particular expression here, and we're going to square both sides. Okay? So 2 is going to be equal to p over q squared, which is equal to p squared over q squared, as you can square both the numerator and the denominator individually. Therefore, we get p squared is equal to 2q squared. So what this is saying is that p squared is even, as it is of the form q squared times 2. So 2 squared is q squared is some integer, and you multiply that times 2, and that's going to give us p squared. Okay? Therefore, p squared is even, and by our assumption above, since 2 will divide p squared, 2 will also divide p. Okay? And that little vertical line just means divide. So it means it divides it evenly, meaning there's no remainder when you divide them. Okay? So we have p is even. Now, what this means is that we can write p in the form of 2k, where k is some integer. Okay? So what we're going to do is we're going to take this result and this result, and we're going to combine them. Okay? So since p is equal to 2k and p squared is equal to 2q squared, we will plug 2k in for p. So that's going to give us p squared is equal to 2k squared is equal to 2q squared. Okay? And we can go ahead and square what's inside the brackets here. So this is going to give us 4 times k squared is equal to 2q squared. Now we can simplify this a little bit, and that's going to give us 2k squared is equal to q squared. Now this looks familiar because this is very similar to what we had up here. Okay? So what this is saying is that q squared is even. Okay? So because we have k squared, which is some integer, okay, times 2, that gives us q squared. Thus, q squared is even. And this means that 2 divides q squared. But this also implies that 2 divides q. Okay, so this means that q is even. So we have p and q are both even, and this means that 2 divides p and 2 divides q. Okay, now this sort of creates a problem because we assumed above that the greatest common divisor of p and q was equal to 1. But now we're seeing that 2 divides both p and q. And because 2 divides both p and q, and 2 is greater than 1, this creates a contradiction, meaning that the greatest common divisor of p and q cannot be 1. And this means that the square root of 2 cannot be an element of the rational numbers, meaning it cannot be written as p over q. Therefore, we conclude that square root of 2 is not an element of the rational numbers, and square root of 2 is irrational. Okay, I hope you guys enjoyed this proof today. If you have any questions, comments, concerns, feedback, I'd love to hear it. And you can leave a comment below. And thanks for checking it out. Have a good one.